Now that we can obtain insolation data, how do we use this information? We can match our roof angle to the empirical values presented here to estimate true solar gain or insolation. Along with the standard values of 0, 90, and latitude, we also have these latitude plus 15 and latitude minus 15 angles. These are listed because they're weighted averages of the angle of the Earth's tilt between each solstice. At the solstices, the Earth's tilt is either plus 23.5 in the summer or minus 23.5 in the winter, and the tilt is 0 degrees at the equinoxes. So the angle between the solar panel and the sun should ideally always be 90 degrees. As the sun is higher in the sky, we would want to tilt the solar panel less, so latitude minus 15 degrees. Whereas the sun is lower in the sky, we'd want to tilt our panel higher, maybe latitude plus 15 degrees. Typically, you can't tilt a solar panel once it's been mounted, except for ground mount or tracking systems. So we generally want to install fixed panels at an angle that collects the most insolation during the entire year. We know that in Colorado Springs, the maximum insolation is available at latitude. So in this case, we'd want the angle to be exactly 38 degrees, which would maximize our insolation capture over the course of the year. We can predict insolation for rooftops that are already there, or design a structure for optimal sunlight collection. The other information that's available in this spreadsheet is tracking information. Apart from fixed tilt, south-facing data, we also then have solar radiation from south-facing one-axis tracking, meaning the panels will track from east to west around a fixed north-south axis, following the sun when it rises in the morning and across the sky during the day to the west at sunset. The north-south axis is still at a fixed tilt, with data available for 4 of the tilt options, also included in the fixed position data, 0 through latitude plus 15. Latitude is still the best overall collector angle at 7.4 full sun hours, almost 2 more hours of full sun on average per year than the fixed position. And if we move to 2-axis tracking, we see even a higher increase up to 7.7 full sun hours, because we're tracking both seasonally north to south and daily east to west. In this location, Colorado Springs has very low cloud cover, so tracking would work pretty effectively. What do we do with these values? Well, these are daily insolation values averaged over the course of the year, or the energy per square meter per day on average. If we know the energy is, say, 5.6 kilowatt hours per square meter per day, and multiply by the number of days per year, we end up getting the annual incoming solar radiation, or insolation, which is 2,044 kilowatt hours per square meter per year. Now we can look a little more closely at specific location where tilts will play a little more important role, such as the Northeast. Specifically, let's look at where I am in Syracuse, New York, where the latitude is about 43 degrees north, which is in the Northern Hemisphere and higher than Colorado Springs. In this case, latitude minus 15, 28 degrees, has the highest in average daily insolation. So if our solar panels are mounted at 28 degrees, we would get the greatest annual insolation. But why does this change geographically? Well, because of tilt and cloud cover, northeast locations have markedly higher solar gain in the summer months, and significantly lower sunlight in the winter months due to the shorter day length and cloud cover. So in this case, by tilting at latitude minus 15, we're optimizing for the summer months where there's the most available insolation. So if we look at several cities across the United States and Canada, we can evaluate yearly averages. Phoenix, Arizona has an insolation of 2,336 kilowatt hours per square meter per year, and the lowest being Seattle, Washington, because of its cloud cover. These numerical values match up to the colors we see on the NREL maps. We'll also come back to using the monthly energy values when we review shade analysis for photovoltaics in future modules. Weather information is the last piece included in the solar database because these are recorded at meteorological stations across the United States. Once we have a little bit more background, we can also start using the PV Watts tool that's available through the National Renewable Energy Lab. And that begins with entering a location and inputting a system size. From there, the system can automatically calculate the expected energy a system will produce with variations in tilt, rotation, and other losses. In the next segment, we'll look at how photovoltaic energy from these data sources can be used to actually design a system from insolation through to output energy.